Hello students, in this lecture we're going back to calculus and we're going to try to develop the derivative of sine function. So if we would like to find the derivative of sine, by definition it's just limit when delta x goes to 0, sine of x plus delta x minus sine of x divided by delta x. But unfortunately, there is not much we can do for this expression. We can't really simplify, cannot do much. So we need to go a little bit sideways. And to go sideways, first thing we're going to do, we're going to develop squeeze theorem. So squeeze theorem is an interesting idea. It's very hard to understand it from words, but when we look at it geometrically, it would be easy to see what's going on. So how does this theorem work? This theorem works like this. We have to suppose that we have the following three functions in this order. G of x is less or equal than f of x is less or equal than h of x for all x close to x equals a, but not equal to a. So we have the situation when the functions are in this specific order everywhere, maybe except a. It's not crazy important at a. What else do we have to suppose? We have to suppose the following. If the limit of g of x, the function on the left, when x approaches a, is equal to the limit of h of x, the function on the right, when x approaches a, is equal to some number L, so they're the same quantities. Then what can we say about the limit of the middle function? Then the limit of f of x when x approaches a is also equal to L. So this is a very great outcome. Let's see visually what's going on. Visually, we have this situation. We have some number L over here. It's on some number L. And on the top, we have the function which is h of x. It's bigger than all of them. Suppose this is your a. And our h goes something like this. And the limit at a is equal to L. And on the bottom, and let me write it, it's h of x. Then on the bottom, we have some kind of a function g that also has the limit L, and this is our g function. And our function f goes somewhere in the middle. It's this is our f function. So you can see that h is bigger than f, and f is bigger than g, and g and h have the limit L at a, then function f also has the same limit in the middle. Okay, so why this squeeze theorem is so good? Let's try to look at the following example. Not example, but an idea that we're going to use. This is a very hard limit to calculate. Limit of sine of x over x when x approaches 0. So why is this limit so hard to calculate? Because it's not really clear what's going on. Sine of 0 is 0, so we have 0 over 0 if we use direct substitution. But we can't really simplify, cannot do anything at all. All right, so we'd like to find this limit. But before we do that, we have to do a little bit of review. And our review is about a sector. So sector is just a piece of a circle. Sector is a piece of a circle. And the circle has radius r, angle theta, radius r. And if we think about the area of the sector, we can say that the area of a sector, A is equal to 1/2 r squared times theta, where theta is in radians. Has to be in radians. You cannot use degrees. All right. So what else do we need to review? We also need to review if we have some point x and y on the plane, and we connect it with the origin, and if this distance is 1 and we're dealing with the unit circle, let me try to do it one more time. Okay. So if we're dealing with the unit circle with radius equal to 1, then we can build this triangle over here, and the area of this triangle over here, what would it be? The area of this triangle will be 1/2 x times y. But if you remember, for the unit circle, x is the same as cosine of theta, if this is angle theta, and y is sine of theta. So we can think of the area of this triangle as 1/2 cosine times sine of theta. Right. So base times height, but base is x, height is y, and they equal cosine and sine respectively. So now we're ready to build this very important geometric construction. So I'll make a big picture over here. So we take a unit circle. And in this unit circle, we measure angle theta. So we measure angle theta over here. This is angle theta. This is the triangle I was talking about. And here in red, we have the area of this sector here. We also have this distance to be x, and this distance over here to be x. And this is a 90-degree angle. So let's start building it. What is the area of this sector? Area of this sector in red, A, is gonna be 1/2. And what is this distance over here? That's a unit circle. So this is length 1, this is length 1. So it's 1/2, 1 squared times theta. And if we simplify it, we're going to get theta over 2. Now, what is the area of this rectangle in black? So the area of this rectangle is A equals 1/2 x times y, which is 1/2 cosine of theta times sine of theta. Right, so this is relatively simple. Now the last piece for this construction. So what we're going to do, we're going to go to this point and we're going to measure radius x, and we're going to create a circle of radius x. And we're going to look into this sector over here in blue. And this sector in blue, so the area of this sector in blue, area of this sector equals. So what do we need? We need what? We need 1/2 radius, and radius we took was x. So it's going to be 1/2 of x squared times the angle, but the angle is the same theta as before. And from this geometric construction, we can clearly see that the area in blue is always less or equal than the area in black, and less or equal than the area in red, just from the geometry here. So what is the area in blue? The area in blue is 1/2 x squared theta. The area in black is 1/2 cosine of theta sine of theta, and the area in red is 1/2 of theta. 1/2 of theta. So in each part we have 1/2, 1/2, and 1/2, so we can divide by 1/2, 1/2, and 1/2. This is clear. And we're left with x squared theta less or equal than cosine of theta sine of theta less or equal than theta. So what are we trying to do actually here? Let's go back and see what we're trying to achieve. We would like to find the limit of sine of x over x. Sine of x over x. So we already have sine over here. So we need to have x on the bottom. Our variable is theta, so I'll divide everything by theta. So theta and theta goes away, theta and theta goes away. So we're left with x squared less or equal cosine of theta, then sine of theta over theta less or equal than 1. All right. So I'm having this cosine of theta, which I don't really want. I just want this quantity in the middle. So I'm going to divide everything by cosine of theta. Cosine of theta and cosine of theta. So these quantities go away. Right, so finally, what is x squared? Remember, x on the point xy, on this point xy, x is also represented by cosine of theta. So that means I can substitute x by cosine of theta. So I'll have cosine squared of theta over cosine of theta on the left. In the middle, I have sine of theta over theta. And on the right side, I have 1 over cosine of theta. So one of these quantities goes away. My final inequality is this. So and that's where its shape exactly fits the squeeze theorem. So what do we need to do to use squeeze theorem? In order to use squeeze theorem, we need to calculate the limit of the left side. So what is the limit of cosine of theta when theta approaches 0? And by direct substitution, we just have to find cosine of 0, and cosine of 0 is 1. We also need to calculate the limit of the right side and see if it's going to be equal to 1. So limit when theta goes to 0 of 1 over cosine of theta. Again, by direct substitution on the bottom we get 1, and so it's 1 over 1, so it's also 1. And since the left limit of this function is 1, and the right limit of the function on the right is 1, we can say that by the squeeze theorem, limit of sine of theta over theta when theta goes to 0 is equal to 1. But it doesn't really matter which variable we write. We can also write a limit of sine of x over x as x approaches 0 is equal to 1. Doesn't really matter which variable we're going to use. All right, so we established this result. Let's use it in a short example, which you'll have to do a few of those at home. They are not trivial, but not really hard. Suppose we would like to find the limit of sine of 3x over x when x approaches 0. So we can clearly see that in the sine we have 3x. So that's the quantity that is inside of the sine. So what I can do, I can write 3 over here, and then we'll have the same quantity in both places. But if I wrote something in the denominator, I have to write the same thing into the, I wrote it in the denominator, so I have to write it into the numerator. But according to the rules of the limit, 3 can also be moved up front. So we'll have 3 limit x goes to 0, sine of 3x over 3x. Now, let's try to think. When x goes to 0, x is really small number. What happens to 3x? 3x will also be a small number. We've done this example a long time ago, a few weeks ago. So basically, when x goes to 0, 3x also goes to 0. Right? Imagine you take number 0.000000001, you multiply it by 3, you will get number you will get a number 0.0000003, which is also pretty close to 0. And we know from this rule that this quantity goes to 1, so behavior is 1. So our answer for the limit is also 1, but we have this number 3 here. So it's 3 times 1, which is 3. So that's the use of this hard limit. Unfortunately, we need to prove another hard limit. So second hard limit is about cosine. We did one about sine, but now hard limit for cosine. So we would like to show that the limit of cosine of theta minus 1 divided by theta when theta goes to 0. What's wrong with this limit? Because if we use direct substitution, and plug in 0 for theta, what it will do to us? Cosine will be equal to 1, so we'll have 1 minus 1, which is 0, so it will be 0 over 0. Not really good. So how can we solve this limit? This one is a little bit easier than the one before. We can rationalize the numerator. How do we rationalize the numerator? We multiply by the conjugate. I said rationalize, that's the wrong statement. I was just going to multiply by the conjugate. So how do we create conjugate? We take the sign, we switch it to an opposite, and that would be the conjugate. So cosine of theta plus 1, and since I did it to the numerator, I'll do the same for the denominator. So I multiply denominator by the same quantity. So what do we get in the numerator? We get limit theta goes to 0, so we have cosine theta minus 1, cosine theta plus 1. What does it mean for us? It's a minus b times a plus b. So it's a difference of squares. We're going to get cosine squared of theta minus 1 squared. And on the bottom, we get theta times cosine of theta plus 1. So let's try to see. 1 squared is just 1. So we have limit cosine squared of theta minus 1 divided by theta times cosine of theta plus 1. That's what we have gotten. And what is cosine of squared minus 1? So let's try to think. We know that 1 is equal to sine squared of theta plus cosine squared of theta. That's our famous identity. So that means for 1, we can put this quantity over here. And theta obviously goes to 0. So we have limit theta goes to 0, we have cosine squared of theta minus parenthesis sine squared of theta plus cosine squared of theta. Again, instead of 1, we plug in the quantity. And on the bottom, we have theta times cosine of theta plus 1. So we open up the parentheses, we get limit theta goes to 0. We have cosine squared of theta minus sine squared of theta minus cosine squared of theta. We distribute the minus, so it's going to be negative quantity. There's going to be negative quantity divided by theta times cosine of theta plus 1. So this cosine squared and this cosine squared add up to 0. And this negative 1 is a constant, so we can move it up front. So minus goes up front. We have limit theta goes to 0. We have sine squared. Sine squared of theta. Sine squared of theta divided by theta times cosine of theta plus 1. So now mathematical trick, right? Mathematical trick, that's why it's called hard limit. So I'm going to rewrite this quantity in a very special form. I'm going to write it like this. I'm going to split sine squared into sine times sine. So first expression, we have a sine of theta over theta. So this theta we use and one of the sines we used. Then we have one more sine divided by cosine of theta plus 1. What do we know about this? Sine theta over theta, when theta goes to 0, this goes to 1. Then this quantity over here on the bottom, if we plug in 0, we're going to get 2. But numerator is 0, right? So if we use direct substitution for this one, we're going to get 0 over 1 plus 1, which is 0. So this means this term goes to 0. And if we multiply 1 and 0, we're going to get 0. So we calculated this hard limit, and we now know that limit of sine of theta minus 1 over theta when theta goes to 0 is equal to 0. So second hard limit we solved. So it was a long preparation, but now we're ready to do the derivative of sine. So derivative of sine. Derivative of sine. Okay, let's do this. So we have sine of x quantity derivative, which is the limit delta x goes to 0, sine of x plus delta x minus sine of x over delta x. Now we're going to use the rule for the sign of the sum. All right, so what is the identity? Identity says that if you have a sine of alpha plus beta, that's going to be a sine of alpha cosine of beta plus cosine of alpha sine of beta. So we're going to use this identity. We have limit delta x goes to 0. So let's do this out. The first term, sine of x cosine of delta x plus cosine of x sine of delta x minus sine of x. That's the numerator. Denominator has delta x in it. So let's look quickly. At the end we have sine of x, and the only other term that has sine of x is the first term. Look, this term over here has sine, and this term over here has sine. So we're going to put them together and write it as one fraction. So we'll say limit delta x goes to 0. Our first fraction is sine of x cosine of delta x minus sine of x divided by delta x at the first fraction, then this plus, then the limit delta x cosine of x sine of delta x divided by delta x. So what did I do? I used the rules for the limit that says if you have a limit of the sum, it's the sum of the limits. So we split the fraction into two parts, and then we apply this rule. And we have equal, equal. So sine of x and sine of x, it doesn't depend on delta x because delta x is the variable for the limit. So it's a common factor. We're going to factor and we're going to put it outside. So it's going to be sine of x over here. And we're left with the limit delta x goes to 0. What's left inside? Cosine of delta x minus 1 divided by delta x. And this is one of our hard limits. We know this quantity goes to 0. That's the beauty of it. Let's look at the second expression here. So cosine doesn't depend on delta x, so we can put it outside. All right, we're going to put it outside, and inside we have limit of sine of delta x, sine of delta x over delta x when delta x goes to 0. But that's our second hard limit. We know this hard limit is equal to 1. So this first expression just 0, and the second expression is just cosine. Conclusion, so it's equal to cosine of x from here, times 1. Conclusion, if we take derivative of sine, we're going to get cosine. That's the rule that we have gotten after such a long lecture. So let's do a few examples to finish this off. First example we're going to do is asking us to find derivative of sine of x to the 5 derivative. So since we don't have just regular x inside, we have to apply chain rule. We have to apply in chain rule. So let's see what is an inner function, what is an outer function. If we plug in x over here, we would have to raise it to the 5, and at the end we would have to apply sine. So sine is our outer function. So chain rule says take derivative of the outer function, so derivative of sine is cosine. Put your inner function inside and multiply by the derivative of the inner function. So there is no prime over here. We rewrite this expression and we calculate derivative of x to the 5, which is 5x to the 4. And that would be our answer. Maybe we will write it as 5x to the 4 cosine of x to the 5. And then the next example that we're going to do, the last one for this lecture, is the following example. That what do we need to do here? We need to calculate derivative of sine to the 5 of x, sine to the 5 of x derivative. So now, what's the difference between these two things? First of all, it's an abuse of notation. Even though we have number 5 over here, we actually mean that it's sine of x raised to the 5th power. And then we need to find derivative. So let's try to plug in x to just understand what's going on. If we plug in x, then we calculate sine, then we raise it to the 5. So this power is our outside function. So according to the chain rule, we need to use the power rule first. 5 goes down, then we have something to the power 4, and this something is sine of x. And then we have to multiply by the derivative of sine according to the chain rule, right? Chain rule forces us to do that. So we have 5 sine to the 4 of x, if we use abuse of notation again. And then we write the derivative of sine, which is cosine. And that's our answer for this exercise. We'll do way more trig functions in the future. You will practice at home. I hope it will be a little bit more clear, but again, chain rule is the hardest rule we learned this semester. And I'll see you in the next lecture.